So, hello everyone, this is lecture 6 for the nuclear physics. In the last lecture, we were discussing about the binding energy and we were seeing this curve. And I told you what observations we took from this curve. Now, today, we will try to explain this curve and how we will explain. Now, see, Bohr gave this model, means he compared this nucleus with the liquid drop, and that's how he tried to explain this. And that was very good explanation actually. So how we explain? See, liquid drop you have seen that we know that when you have water and then there is molecules on the surface of the water, they are very easy to evaporate because they have non-equilibrium forces on that surface particles, and inside particles are very hard to remove. So similarly, he compared this with the nucleus. Means initially, if you have some this kind of nuclei which have your four nucleons or two nucleons, then they are totally on the surface and they will be very easy to remove from this each other, and there will be less binding energy per nucleon for each of them. See, and how you can find this? So it will be E1 plus E2 plus E3 divided by 4, means there will be 4 nucleon, but last one won't require any energy. That's why we take 3 energy and divide by 4. So this will give you binding energy per nucleon. But see, as number of nucleons increase, so there will be some nucleon which come inside this. So when nucleons come inside it, then there will be more energy required to remove them. Now see, these nucleons inside this which will have the more energy required to remove. So this higher terms will give the average high value binding energy per nucleon. That's why when initially this start to increase, so A start to increase, so this graph suddenly increase. So that is the reason behind it is behind this binding energy by nucleon increase. That's why this. So this is the liquid bottle. So it is always easy to remove the nucleons present on the surface as compared to the nucleon which are well inside. This idea was given by Bohr in which he compared the nuclei with the liquid drop. Due to this reason, on the lighter nuclei side, as A increases, binding energy per nucleon will increase significantly because number of well inside nucleons as compared to nucleons present on the surface, they will increase. So that's why, as you will see, A increase, so N inside will increase as compared to N surface. So this ratio will increase. That will give you a sharp increase in the binding energy per nucleon. But see, there is the second thing that what happen when this A increase very much, then there will be more number of protons comes inside. So proton will repel each other, and now that repulsion will affect the binding energy. How? See, as A increase, number of proton will increase. So protons are positively charged particles, so there will be electrostatic potential repulsive energy. So this will disrupt the stability. So if stability of nuclei decrease with this increase in the number of protons, that means binding energy will decrease per nucleon. Means less energy will require to break this because it is already going in the non-equilibrium state because of this repulsive forces. So that's how, means when the number of protons will increase, so it must means this increment in the binding energy must slow down. So that's what you see here, that this is starting to slow down like this. Now so let's try to explain the other terms also later on. Sorry, here it is. As a number increases, number of positive charged protons inside a nuclei will also increase. There will be repulsive force between them, which will reduce the stability of nuclei. As a result, binding energy per nucleon should decrease. So as I told you, already told you. Now see, as binding energy per nucleon should decrease, so why it is not decreasing sharply? Means it this graph is very gentle, not like it is dropping like this as the protons are increasing. So this must go like this, but why it is going this slow? So see, after the 40 atomic number, you will see that there will be, yes, protons are increasing, but see, neutrons are also increasing, and neutrons are more increasing as compared to protons. So after a 20 Ca40, you will see that number of protons will be larger as compared to proton, and there will be not only this electrostatic interaction, but there will be this strong interaction comes into the picture. That is always attractive, and that is between proton neutron, neutron. This will be more dominant there, and but this factor will always play the role that the repulsive. That's why this graph will become gentle but not drop sharply. This will be gentle like this, as we see here. This will be like this, not like this. So that was the reason behind this. And now see, there what I just told you. Here's the explanation. As a number increases, then not only protons, number of neutrons also increases after 40 Ca20. Number of neutrons become greater than protons. As a result, contribution of a strong interaction between proton neutron and neutron neutron will start increasing, which is attractive in nature. This feature provides some stability to the nuclei, and slope of the binding energy curve on the higher A side becomes gentle. Some other facts about nuclear stability. Now see, there was this survey or you will say that observations, experimental observations, when the protons and neutrons are even, and then we find the number of stable nuclei. So there we find that 163 nuclei are stable. Then for those protons are even and neutrons are odd, so you find that there were 57 nuclei which are stable, and for odd even it was 53 nuclei which are stable, and when both are odd you will find that only 4 nuclei were there which were stable. So from this we find this observation that when there are even nuclei, so that will be most stable nuclei, and with odd there will be least stable nuclei. So what this gives us, that there must be some pairing of nucleons, and pairing means there will be some spin which is anti-parallel. So that's why nuclear spin will also come into the picture, which will be very important to us because of this thing, that we are finding very much stable nucleus for the even. So from this table, one can observe even nuclei are most stable and odd nuclei are least stable. Later on, we find out pairing of nucleons will be major cause for this behavior. In a pair, one particle will have up spin, other have down spin. Thus, this table providing a hint that nuclear spin also plays a role in the stability of nuclei. So that's what just I told you. So we'll see, as in the last lecture we have seen there was this formula for binding energy. There you have the pairing energy also. So that's from this that term came in the picture, that there this pairing is come also. Okay. So it plays a role in the stability of nuclei. Now see, there is one more curve. You will see this is very interesting curve. Now what this curve represents, there is this number of neutrons, there is this number of protons. You just draw a line, and this line is the 45 degree. That means at every point you will see number of neutrons is always equal to number of proton. Now you will draw a curve with the nuclei which are stable, means stable nuclei, and their number of proton and neutron. So there will be coordinates like number of neutrons, number of protons, like this, and you will plot them, means you will plot stable nuclei in this curve. So you will get this kind of curve. You will use some curve fitting, and you will get this kind of curve for the stable nuclei. Then for some unstable nuclei you will plot them. So you will get some unstable nuclei on this side and some unstable nuclei on this side. So this kind of curve you will get. Now see, this is your stable nuclei curve, and these are your unstable nuclei. So there will be some unstable in the left side and some unstable on the right side. So how these unstable nuclei can achieve this stability line? So see, for the left hand side you will say number of neutrons are greater and protons are less, and the right side you will see that number of protons are larger as compared to, means number of protons will dominate as compared to number of neutrons, and here neutrons will dominate as compared to proton. So how they can achieve this stability line? For this side they definitely try to reduce the neutron and turn into the proton, means number of neutron will decrease and proton will increase. So this will reach here. So like this neutron will decrease and proton will increase, because neutron will turn into proton. So this will go like this. So it will come to the stability line. And for the right side you will see that proton is dominant, so proton will convert into neutron, and that's how. And when it is converted to neutron, that will increase one neutron in the nuclei. So this will go like this. So that's how they will achieve the stability. For the right side this will go like, means proton will convert into neutron. For the left hand side neutron will convert into proton. When neutron convert into proton, then you will see there will be beta negative, or the antineutrino particle will be emitted. And for when proton convert into the neutron, so there will be beta negative emission will be there, sorry, beta positive will be there for this, beta negative for this. So let's see. So this kind of, see, when neutron convert to the proton, you will see that it will give the beta negative emission plus antineutrino, and proton will convert into a neutron plus beta positive plus neutrino. For lighter nuclei up to 20 Ca40, number of protons will be nearly equal to number of neutrons, as we can see here. It is like around 40. You will see that it will be remaining same. Proton and neutron will be nearly equal to number of neutron. As A increases, that is for heavy nuclei, the ratio Nn divided by Np increases, means number of neutrons start to increase as compared to proton more rapidly, and approach to 1.5 for heaviest nuclei. If you plot unstable nuclei on the same curve, then these unstable nuclei will be divided into two categories. Some of the will fall on the left side and some will fall on the right side, as I already told you. Unstable nuclei falling on the left side are neutron rich as compared to the stable nuclei. So neutrons in nuclei may convert into the protons to achieve the more stable configuration, and by the following process, beta negative particle or antineutrino will emit. These nuclei are more susceptible to beta negative decay. Now, nuclei on the right hand side of the stability line are rich in the protons, so protons inside the nuclei may convert into the neutrons to achieve the stability by following process. Proton will convert into neutron with the beta positive emission and the neutrino. Nuclei on the right side of the stability line are more prone to beta positive decay. So that is what I just explained. So here we end the basic properties of nucleus. So in the next lecture we will start with the radioactivity. So thank you everyone.